logic needed to unpack the ultimate fantasy stemming from these errors, the singularity itself. But that is a deep dive for another day. Thanks for joining us. Imagine it is a Monday morning in, well, let's say the late 1940s.
Okay, I'm picturing it.
You walk into this incredibly stuffy laboratory and you see these just absolute brilliant minds, right? People like Claude Shannon and Alan Turing.
Right, the absolute titans of early computer science.
Exactly. And they are huddled over one of the very first electronic computers. I mean, these machines are not like the laptop on your desk. They are the size of a literal room.
Yeah, just completely filled with vacuum tubes.
Vacuum tubes everywhere, giving off this immense, suffocating heat. And, what are they actually doing with this unprecedented, world-changing computational power?
Well, they're playing chess.
They are playing chess. It's this pure intellectual curiosity and exploration of logic in games.
Right, it's almost playful.
But then, imagine you walk into that exact same room on a Tuesday.
Okay.
The chessboard is completely gone. Instead, you have scientists like John von Neumann feeding data into that exact same machine. But they aren't playing games.
No, definitely not.
They are using it to calculate nuclear blast radii. They are using the exact same silicon and wire, well, vacuum tubes and wire, to figure out precisely how much fissile material is required to vaporize an entire city.
Yeah, chess algorithms on Monday and then just absolute mega death on Tuesday.
It is the ultimate whiplash.
It really is. And that specific historical moment, it's like a pressure cooker. Because, we often look at the modern hype surrounding artificial intelligence, and we just assume it was born in Silicon Valley, like, I don't know, 5 or 10 years ago.
Right, with an app update or something.
Exactly. But to actually understand this intense obsession we have with AI today, specifically this grand idea of the singularity, where machines supposedly become infinitely smarter than us, we really have to start in that sweltering room in the 1940s.
Because that dual nature of early computing power, it created this very specific atmosphere, right?
Yeah, it was this profound existential dread mixed with just absolutely limitless possibility.
And that is exactly what we are going to completely deconstruct today. Welcome to our deep dive. Today, our mission is singular.
No pun intended, right?
All right. We are doing an intensely detailed step-by-step analysis of Chapter 4 of our source text, which is titled The Singularity Then and Now.
We're basically going to break down where the actual math of this concept comes from.
Yeah, and how it got hijacked by modern futurists. And crucially, why the actual grueling reality of computer science labs looks entirely different from the utopian or, dystopian promises we keep hearing in the news.
It's a huge gap. But before we get to the AI taking over the world, we really need to back up.
Because the 1940s didn't just happen out of nowhere, right?
Exactly. We need to look at the 300 years of technological acceleration that literally paved the way to that specific moment.
The text introduces this historical phenomenon of symbiotic power.
Right, symbiotic power.
Okay, let's unpack this because it's a great term. How does that compounding loop actually work in practice?
So symbiotic power is basically the idea that scientific discovery and technological invention, they aren't on separate tracks.
Okay.
They are a continuous, ever-accelerating feedback loop. So science seeds a new piece of technology.
Right.
And then that new technology is immediately used to uncover even more science, which then creates even better technology.
It's like a snowball rolling downhill.
Exactly. The text uses a really classic historical example for this, which is optics.
Oh, yeah, the telescope.
Right. So you start with theoretical science, giving us a very basic understanding of how light refracts through glass.
Just the raw physics of it.
Right. And that basic understanding allows engineers to build a physical piece of technology, right? The telescope.
And the telescope isn't just a neat little gadget for, bird watching. It completely shatters our entire understanding of astronomy.
Precisely. You point that new telescope at the sky, and suddenly the science of astronomy leaps forward centuries in just a matter of a few decades.
Because you suddenly realize, oh, wow, the Earth actually isn't the center of the universe.
Right. You have Galileo looking at the moons of Jupiter. And that influx of new, shocking astronomical data suddenly demands even better optical calculations.
Which forces the underlying science of optics to improve.
Exactly. Which leads to better lenses, which then eventually leads to a totally different application, the microscope.
Wow. Okay. So now you aren't just looking at stars, you're discovering bacteria.
Yeah. The fruits of science literally create the physical tools required for better science. It is essentially a compounding interest curve, but it's applied to human knowledge.
And I think this is a really important point the text makes. This isn't just some sterile academic exercise happening in a vacuum, right?
Oh, not at all.
This technological loop is incredibly disruptive and honestly incredibly violent when it actually hits human society.
It's chaotic.
Yeah. You trace this through the 18th and 19th centuries in the text, and the social chaos is just staggering.
We'd invent the steam engine and then later the internal combustion engine.
And suddenly, all human labor is completely upended.
Right? You have these exploding city populations, people migrating by the millions into these dense urban centers just to work in factories.
And with that rapid urbanization comes, incredible squalor, disease, and entirely new forms of social injustice.
The machinery literally dictated the geography and the sociology of the entire human race.
It wasn't just a convenience.
No, steamboats, trains, trolleys, they didn't just make travel faster. They created these massive global trade networks that destroyed old economies and birthed entirely new ones, practically overnight.
I mean, entire classes of people were shifted from agrarian lifestyles, which were governed by the seasons.
Right, waking up with the sun, harvesting in the fall.
Exactly. They were shifted from that into these very rigid, clock-regulated industrial workforces. The psychological toll of that shift just cannot be overstated.
And it shifted human behavior on a microscopic, deeply personal level, too.
I always think about Thomas Edison here and the incandescent light bulb.
Oh, yeah. That's a perfect example.
Because we usually treat the light bulb as this quaint, happy symbol of a bright idea, right? Like a cartoon character with a bulb over their head.
Right, exactly.
But think about the absolute biological arrogance of it. For the entirety of human history, we were entirely beholden to the sun.
When it got dark, you basically stopped working.
You went to sleep. You sat by a fire. But Edison comes along, flips a switch, and says, actually, no, we are decoupling the human race from the solar cycle.
It's a profound shift. And the text points out this incredibly stark, almost amusing reality that suddenly, rural insomniacs could spend their nights reading Dos Capital or On the Origin of Species.
I love that specific detail, just sitting up at 2 a.m. reading Marx because you finally have a light bulb.
Right. I wouldn't frame it just as arrogance on Edison's part, though. I'd frame it as a fundamental re-engineering of the human day.
Okay, yeah, that's a good way to put it.
Because illuminating text at 2 in the morning completely changed the pace of political and scientific thought. People literally had more waking hours to consume complex revolutionary ideas.
And because of all these advancements, we saw productivity absolutely soar.
Wealth and health increased across the board, globally. The average human lifespan began to climb significantly.
But, and here is the really dark turn the text takes, if we look at the historical record, that acceleration had a very dark twin.
It absolutely did.
Blood and violence scaled right alongside the health and the wealth.
Yeah, it's like
a mechanic who keeps putting a bigger and bigger engine in a car but completely forgets to install a steering wheel or brakes.
that's a great analogy. The faster humanity went, the more catastrophic our collisions became.
And this brings us right to World War I. Because this wasn't just a traditional war of cavalry and muskets.
No, this was the pure industrialization of slaughter, mass chemical warfare.
Right. Science gave us the Haber-Bosch process.
Which is fascinating because that process allowed us to synthesize fertilizer from the air, basically, and feed billions of people.
It's a miracle of science.
It is. But that exact same scientific infrastructure also gave us chlorine gas, which was used to suffocate an entire generation of young men in the trenches.
Which loops us right back to our starting point in the 1940s, in that sweltering computer lab.
Exactly. Because the culmination of this entire 300-year feedback loop is the ultimate inflection point, the nuclear bomb.
The bomb proved, beyond any shadow of a doubt, that unbridled technological innovation carried a literal existential price tag.
The dystopian possibilities just weren't hypothetical anymore. They were suddenly measurable in megatons of explosive force.
Which brings us back to John von Neumann sitting in that room with the early electronic computer. Chess on Monday, blast radii on Tuesday.
And we have to understand who von Neumann was. He wasn't just a casual observer or some mid-level engineer.
Right, he was a legend.
He was an absolute polymath. He was universally respected by all his peers, including people like Alan Turing.
So when von Neumann observed a trend, the entire scientific community took notes.
Exactly. And in the 1950s, he had this really pivotal conversation with another mathematician named Stanislaw Ulam.
And this conversation is essentially what birthed the concept of the singularity as we discuss it today, right?
Yes, Ulam actually recalled von Neumann looking at this ever-accelerating progress of technology, and concluding that it was approaching some, and this is a direct quote, some essential singularity in the history of the race.
An essential singularity in the history of the race.
And von Neumann went on to describe it as a point beyond which human affairs, as we know them, could not continue.
Okay, I really want to isolate that specific phrase. Beyond which human affairs, as we know them, could not continue.
That's a heavy statement.
It is. And to truly grasp the weight of that, we have to look at it through the lens of von Neumann's actual profession, because he was a mathematician.
Right, he wasn't a poet.
Exactly. When he uses the word singularity, he is not using it as some flowery metaphor for change. He is invoking a very specific structural concept from mathematics.
Okay, so let's break that math down for the listener.
Yeah, because my math is a little rusty, to say the least. So let's talk this out. If I take my calculator right now and I try to divide a number by 0...
It flashes an error message. It just gives up.
Right, it says undefined or just breaks. So is von Neumann basically saying that human history is going to hit a societal divide by 0 error?
That is actually a highly accurate way to look at it, yes. In mathematical analysis, a singularity is literally a point at which a given mathematical object or a function becomes undefined.
It just stops working normally.
Exactly. It fails to be well-behaved in a particular way. Usually, it's a value exploding to absolute infinity.
Or like an asymptote on a graph.
Perfect example. Think of a line curving upward on a chart, getting closer and closer to a vertical axis. But the value becomes infinite. It goes straight up.
Right.
At that point, the normal rules of the mathematical model completely break down. The equation can no longer provide a usable, predictable output.
So von Neumann takes this strict, rigid mathematical concept of an asymptote of literal infinity, and he just maps it directly onto human history.
He does. He is formally hypothesizing that technological progress is literally approaching mathematical infinity.
And what's fascinating here is the profound implications of that. I mean, it represents an absolute epistemological cliff edge for humanity.
Yes, because in human history, we have always relied on the past to predict the future.
Right. It's how we plan anything.
If an ancient society discovers metallurgy, we can safely predict that within a few decades, they will make stronger plows for farming and sharper swords for fighting.
That's a logical step.
But if the rate of technological progress accelerates infinitely, the fundamental nature of reality changes so fast that human cognition literally cannot keep up.
It becomes an eschatology. An end of times.
Yes.
And not necessarily an apocalypse where the planet explodes like the Death Star, though, with the nuclear bomb. That was obviously a highly relevant fear at the time.
Very relevant, yeah.
But it's more about an end to history as we can possibly comprehend it.
It creates a total crisis of prediction. If progress hits infinity, no known human methods, no existing thoughts, no strategies or actions can be applied to the world that comes after that point.
Because the variables are changing too fast to track.
Exactly. You cannot strategize for a post-singularity world because your biological brain is incapable of modeling the variables. Prediction itself becomes a physiological impossibility.
Wow. So we have this terrifying, completely undefinable mathematical horizon looming in the 1950s.
Looming over the smartest people on the planet.
Right. The smartest minds are looking at this theoretical graph, watching the line go straight vertical into the complete unknown.
It's a terrifying realization.
But, and this is where I think the text gets really interesting, how does that Cold War mathematical anxiety transform into the Silicon Valley tech dogma we hear today?
That is the million-dollar question.
Because how do we get from a math equation breaking down to a CEO saying, AI is going to take our jobs and become a god?
Though that mutation in the concept begins a couple of decades later with a researcher named I.J. Good.
Okay, I.J. Good.
Good made this crucial foundational pivot. He identified the digital computer as the specific, tangible mechanism that would actually drive us into this mathematical singularity.
So he looked at the computer and said, that box on the desk, that is the engine of the eschatology.
Exactly. It was no longer an abstract historical trend of, like, general technology improving. It was specifically the machine sitting on the desk that was going to do it.
And once the computer is identified as the vehicle for this event, it kind of opens the door for someone like Werner Vinge to step in.
Yes, Werner Vinge is the one who really bridges the gap between pure math and science fiction.
Vinge is such a fascinating character in this history because he was a legitimate computer scientist at UCLA.
Right, he had real academic credentials.
But he was also a Hugo Award-winning sci-fi author.
A very successful one.
So he takes this abstract concept and formally introduces the actual term singularity into the broader field of artificial intelligence in 1986.
And he largely did that through his sci-fi novel, Marooned in Real Time.
Right. But he didn't just leave it in the realm of paperback fiction, which is why we're actually talking about him today.
No, he didn't. In a subsequent technical paper, a paper written for NASA, mind you, Vinge, directly channeled I.J. Good and made this chillingly specific prediction.
Okay, what was the prediction?
He formally stated that within 30 years, humanity would possess the technological means to create superhuman intelligence.
30 years.
And the very next sentence of his paper is the absolute kicker. He wrote, "Shortly after, the human era will be ended."
The human era will be ended. I mean, he is explicitly calling back to von Neumann there.
Absolutely. He's echoing that end of history sentiment.
Let's look really closely at how Vinge phrased this in that NASA paper because the language is important. He says it is a point where models must be discarded and a new reality rules.
Discarding the models, right? The prediction crisis.
He writes that this event will loom vaster and vaster over human affairs, but, and I find this specific part really fascinating, he says, when it finally happens, it may still be a great surprise and a greater unknown.
It is the ultimate blind spot. You can see it coming, but you can't see what it is.
Right. So Vinge basically gives the mathematical fear a face and a timeline. Superhuman AI within 3 decades.
And because Vinge was a respected computer scientist, as we noted, this carried real weight.
It wasn't just some guy writing pulp fiction.
Exactly. It provided a veneer of academic respectability to what was essentially a catastrophic science fiction plot.
Which perfectly sets the stage for the most famous or, perhaps infamous evangelist of this entire concept, Ray Kurzweil. Yes! Ray Kurzweil.
If Vinge introduced the concept to the computer science community, Kurzweil took a massive megaphone and just shouted it to the entire world.
He really did. By the late 1980s, Kurzweil had basically become the ultimate bulldog for the singularity.
He took this niche academic anxiety and transformed it into a massive pop culture phenomenon.
And he did this through a relentless, really aggressive series of publications.
Yeah, let's walk through those. In 1990, he published a book called The Age of Intelligent Machines. Then, in 1998, he escalated the rhetoric with The Age of Spiritual Machines.
Spiritual machines.
Right. And then, in 2005, he reached peak confidence with his massive bestseller, The Singularity is Near.
Just look at the progression of those titles.
It's quite a trajectory.
From intelligent to spiritual to it is happening right now, get ready.
Yeah, the urgency just keeps ramping up.
But Kurzweil isn't just a philosopher, though. He built this entire futuristic empire on a highly specific interpretation of history.
Right. He leans entirely into this concept of exponential innovation.
Okay, let's walk through his logic here step by step, because it's the foundation of his whole argument.
So Kurzweil argues that technological history is fundamentally misunderstood by the average person because our brains are wired to think linearly.
Right, like 1 step, then 2 step, then 3 step, a steady pace.
Exactly. But technology, he claims, doesn't move linearly. It moves exponentially, meaning the time between major paradigm-shifting innovations doesn't stay the same. It actually shrinks as a function of time.
So the sprint keeps doubling in speed?
Yes.
Let's actually linger on a specific historical timeline from the text to really feel the weight of this argument, because it makes a lot of sense when you map it out.
Sure, the paper example is a good one.
Yeah, look at the invention of paper. Paper appeared in China roughly in the 2nd century.
Right.
And it totally revolutionized human memory, bureaucracy, tax collection, everything.
It was a massive leap forward.
But then we just waited. Humanity lived, breathed, fought massive wars, built empires, and died for roughly 1,200 years before Johannes Gutenberg introduced the printing press in Europe around 1440.
1,200 years.
1,200 years between 2 major information technologies. Think about what it means for an entire civilization to go a full millennium without a significant upgrade in how they store or distribute data.
It is a staggering historical plateau.
But then you look at the 20th century, and those massive gaps just collapse.
Right, the timeline compresses.
Computation as a practical electronic technology appears in the 1940s.
Or the 30s, mathematically speaking, with Turing.
Right, and then the internet, this massive global species-altering communications network, shows up less than 30 years later.
The contrast is unbelievable. 1,200 years for a printing press, 30 years for a global computer network.
If you plot that on a graph, the curve is violent. It's almost a right angle.
It is. And if you are Kurzweil, and you follow that violently collapsing curve to its logical conclusion regarding artificial intelligence.
Then human-level intelligence in a computer is not centuries away.
No, it's practically tomorrow. Because the timeline compresses so fast, the leaps in progress happen almost simultaneously at the end of the curve.
And this is where Kurzweil makes his boldest move, right? Here's where it gets really interesting. He didn't just point out a historical trend of shrinking gaps.
No, he went much further.
He codified it, he branded it, he named it the Law of Accelerating Returns, or LOAR.
OAR, the Law of Accelerating Returns.
Let's be totally honest for a second. He calls it a law, which makes it sound like gravity or, thermodynamics.
Right, like an immutable force of nature.
But it's a marketing term. The text explicitly notes it is not a scientific law at all. He basically looked at a chart of historical events, subjectively decided which inventions were major enough to count, plotted them out, drew a line, and branded it a law.
I mean, I wouldn't frame it entirely as a conscious marketing scam because I think Kurzweil genuinely believes the underlying mathematics of exponential growth apply to human invention.
Sure, he's a true believer.
But your skepticism is completely warranted based on the source text. Calling it a law implies a constraint to the physical universe, which it isn't. It is, in reality, a highly selective historical observation.
But Kurzweil uses this law as a foundational premise to argue an incredibly concrete timeline for the future.
He does. Based on LOR, he predicted fully human-level AI would arrive by the year 2029.
2029. We are practically staring down the barrel of that year right now.
We are very close.
And his prediction doesn't just stop there. He claims that once we hit human-level AI in 2029, these machines will begin bootstrapping themselves.
Right. Recursive self-improvement.
Exactly. They will redesign their own code, improving themselves without any human intervention, faster and faster, until we reach artificial superintelligence by the year 2045.
2045 is his absolute date for the singularity. It is the crossover point.
The moment where biological humans are permanently demoted to the second smartest entities on the planet.
Exactly. From that exact year forward, according to him, human affairs as we know them end, and the path of progress disappears into whatever goals the superintelligence decides to pursue.
I want to stop here and just directly ask you, the listener, to really think about this. If you are listening to this right now, 2045 is likely well within your lifetime.
It's only a couple decades away.
Kurzweil is arguing that within a couple of decades, the phone in your pocket won't just be a tool you use to check the weather or scroll social media.
No, it will be a terminal.
It will be a piece of a network that is vastly, unimaginably smarter than you, smarter than your family, smarter than every genius who has ever lived combined.
It's a staggering thought experiment.
How does that change how you view your career, your retirement accounts, your kids' futures? If Kurzweil is right, none of our current human plans actually matter.
And this is exactly where we have to critically examine the source of Kurzweil's authority on this subject.
Because people listen to him.
They do.
Yeah.
He presents this 2045 timeline as entirely, rigorously scientific, backed by his self-proclaimed law of accelerating returns.
Right.
But he also props it up with his very real, very legitimate credentials. He isn't just a science fiction author like Vinge was.
Right. Kurzweil's an actual inventor.
Yes, he helped develop foundational text-to-speech technologies that literally paved the way for systems like Siri and modern voice recognition. He has built actual AI systems.
So when he speaks about the future of tech, people naturally assume he is speaking from the absolute bedrock of computer science.
But when you actually read Kurzweil's broader philosophy, that bedrock starts to look a lot more like a pulpit.
Okay, this is a great transition. Because we move here from his pseudoscientific timelines into the underlying zeal driving his predictions.
The tone completely shifts.
The language he uses to describe the singularity, it moves completely out of the realm of science and into something bordering on theology.
The rhetoric he uses is highly instructive. For example, he doesn't describe the singularity as a complex software deployment or a hardware upgrade.
No, he uses the word merger.
He describes it as a merger between human intelligence and machine intelligence. He calls this merger the cutting edge of evolution on our planet.
The cutting edge of evolution.
He even speculates in his writing that it might be the cutting edge of the evolution of intelligence in the entire universe.
It just gets wilder. He actually writes, and this is a quote, "To me, that is what human civilization is all about. It is part of our destiny."
Destiny.
Destiny. Since when is destiny a variable in a computer science equation?
It's not.
If we look closely at this, I have to ask, is Kurzweil arguing computer architecture, or is he preaching a new silicon-based religion?
The historical and textual analysis in our source material points heavily toward the latter. The prose literally brims with the zeal of a religious convert.
He views technological acceleration not as a tool that humans use, but as a teleological force.
Explain teleological for the audience real quick.
Oh, right. It means a process that has an ultimate predetermined endpoint or goal, like it's moving toward a specific climax on purpose.
Exactly. And because he views this as an evolutionary destiny, he is remarkably, almost aggressively dismissive of anyone who questions it.
Right. If you express any hesitation, if you, say, suggest that maybe we shouldn't build a machine god that obsoletes humanity, Kurzweil addresses you directly.
He does not take kindly to critics.
He says that contemplating stopping this progress or thinking human beings are fine the way they are is merely a misplaced fond remembrance of what human beings used to be.
It is a radical, almost misanthropic philosophical stance.
Misanthropic is the perfect word for it.
He is basically arguing that clinging to our biological humanity, our emotions, our physical limitations, our current form of consciousness, is just naive nostalgia.
Like holding onto a VHS tape in the era of streaming.
Right. In his view, human beings are merely a transitional species. We are a biological stepping stone, undergoing cultural and technological evolution, with the sole cosmic purpose of giving birth to our mechanical successors.
It's the ultimate inferiority complex masquerading as visionary futurism.
That's a sharp way to put it.
We are just the messy biological bootloader for the glorious AI operating system.
Yeah, that's exactly how he frames it.
So, okay, let's recap where we are. We have this soaring exponential promise built up through the 80s, 90s, and early 2000s.
The graph is going straight up.
Destiny is calling, the singularity is near, but now we have to step out of the futurist's armchair and walk into a fluorescent-lit computer science lab in, say, 1975.
Oh boy. Prepare for a reality check.
Because the reality of building these machines is harsh, it's grueling, and it tells a completely different story from Kurzweil's graph.
The empirical backlash to these grand claims is incredibly sobering, because while Kurzweil was drawing these perfect exponential curves on whiteboards, the people actually trying to code artificial intelligence were drowning.
So what does this all mean for the actual science?
Well, by the time Kurzweil published his first major book in 1990, decades of actual scientific work in AI labs had already systematically extinguished the hopes of an inexorable, easy march to superintelligence.
Because building a mind turned out to be profoundly resistant to simple engineering.
Extremely resistant.
Enter Hubert Dreyfus.
Ah, Dreyfus.
Dreyfus was an MIT philosopher, and he became the ultimate gadfly for the AI community in the 1970s.
He was a massive thorn in their side.
While everyone else was promising robot butlers and superbrains, Dreyfus actually looked at the tangible output of the labs, and he published a massive, highly influential dismissal of the entire field.
Dreyfus utilized a very specific theoretical framework, which he actually borrowed from a Hungarian philosopher of science named Imre Lakatos.
Okay, what was Lakatos's theory?
Lakatos had this way of evaluating scientific progress, and Dreyfus looked at the state of AI research through this lens and categorized it as a degenerating research program.
A degenerating research program? I mean, that is an incredibly polite academic way of saying you guys are faking it and totally failing.
Pretty much, yeah.
But what are the actual mechanics of a degenerating program? How do you know you're in one?
So in the philosophy of science, a research program is considered progressive if it constantly makes novel predictions that turn out to be true.
Like it's actually solving new problems and moving forward.
Right, it's discovering new things. But a research program becomes degenerating when it stops making new, successful predictions.
It stalls out.
Worse than stalling out. Instead of moving forward, the researchers start spending all their time, energy, and funding merely adjusting their core theories to excuse and accommodate their past failures.
Oh, wow.
They aren't moving forward at all. They're just building more and more complex rationalizations for why their last experiment didn't work.
It's like a mechanic who has a massive leak in a plumbing system. Instead of admitting that the pipes are fundamentally rotten and need to be entirely replaced, they just keep wrapping more and more duct tape around the joints.
Yes, and they keep insisting that the next layer of tape will finally hold the water.
Dreyfus was pointing out that the entire field of AI was just a massive ball of duct tape.
And the truly wild part is that the computer scientists, at least privately, knew he was right.
They were facing an immense, frankly embarrassing gap between their well-funded press releases and the outright failures happening in their actual labs at places like Stanford and MIT.
Let's actually dissect the specific historical failures that the text uses to prove Dreyfus's point, because the historical record is very clear.
Yeah, let's walk through these. The text provides three distinct, undeniable examples where AI just hit a brick wall.
Right. The first is fully automated high-quality machine translation.
Translation, which seems like it should be easy for a computer, right?
They certainly thought so. In the early 1950s, amidst all the paranoia of the Cold War, translating Russian to English quickly was a top national security priority for the U.S.
And the computer scientists of the 50s looked at translation and thought, oh, this is basically just cryptography.
Right, they thought Russian is just English written in a weird code.
We just need to build a massive dictionary database, map the Russian words one-to-one to the English words, apply some very basic grammar rules, and boom, perfect automated translation.
It sounds totally logical. And they threw massive government funding at it.
But by the late 1960s, what happened?
That massive government funding completely evaporated. The entire program was shut down.
Why?
Because the output was largely gibberish. They discovered, the hard way, that human language is incredibly context-dependent.
A word in Russian doesn't just neatly map to one single word in English.
Exactly. Its meaning changes entirely based on the cultural context of the sentence, the tone of the speaker, historical references, and unspoken idioms.
Rigid, top-down programming rules completely collapsed when faced with the ambiguity of actual human language.
They couldn't duct tape their way out of it.
Okay, the second example is even more foundational to AI, I think. It's the failure to build robots with what we would call common sense.
Right. Early AI researchers assumed they could easily program a machine with the basic deductive reasoning required to, say, navigate a normal room or understand a very basic English command.
Like, go fetch the ball.
Yeah. But they quickly realized that human common sense is actually a massive, completely invisible web of biological assumptions.
How do you code a robot to know that you can pull a piece of string, but you can't push a piece of string?
Exactly. Or how do you code the innate knowledge that if you leave a glass of water on a table, it won't just spontaneously float up to the ceiling?
Right. As human beings, we don't even actively think about these things. It is embodied cognition.
We know water is wet because we have physical bodies that feel wetness.
If you try to write out every single rule of physics and every tiny social interaction into literal lines of code,
The database becomes infinitely large.
and the computer just freezes up trying to run 1,000 calculations just to decide if it should step over a shadow on the floor or try to walk around it.
The real world just proved impossibly resistant to top-down, rigid programming logic.
Which brings us to the third specific failure outlined in the text. Conversational systems, or chatbots, specifically those designed to pass the Turing test.
Right. The Turing test, which was proposed by Alan Turing back in 1950, is this famous benchmark where a machine tries to convince a human judge through text-based conversation that the machine is actually another human.
We've all seen variations of this in movies, but when they actually ran these tests in the 70s and 80s, what did the lab results show?
Well, the machines that quote-unquote succeeded in fooling humans didn't do it because they possessed actual superintelligence.
No, they did it through parlor tricks.
Exactly. Or rather, let's actually take that a step further. It wasn't just simple parlor tricks. It was active psychological manipulation of the human judge.
Wow, okay. How so?
Take a famous program like Eliza. It succeeded mostly by mirroring the user's own questions back at them, sort of like a Rogerian psychotherapist.
Oh, I've heard of this. So if a human typed, "I'm sad today,"
The program was coded to simply identify the keyword sad and formulaically reply, "Why are you sad today?"
tricks and bluffing, the chatbot would deflect questions, change the subject abruptly if it got confused, or even intentionally mimic human typos to seem more authentic.
Right, dropping a comma here and there to look biological.
It's a total facade of intelligence. It is a cardboard cutout of a human mind.
It is. And here is the truly damning part that the text emphasizes. This exact same problem still bedevils natural language efforts in AI today.
Even with all our modern tech.
Yes, we have massive large language models now that are incredibly good at predicting the next word in a sequence based on statistics.
But they still hallucinate facts.
Right, they still completely lose the thread of logic in long conversations because they're still just mimicking the appearance of understanding without actually possessing any internal model of truth.
This is the definitive rebuttal to Kurzweil's exponential graph, isn't it?
It absolutely is. While the futurists were preaching the inevitable godlike destiny of superintelligence in their press releases, the actual engineers on the ground were bogged down in a degenerating research program.
Programming a truly intelligent machine wasn't just a matter of waiting around for faster microchips.
No, it was fundamentally theoretically hard. The sky wasn't falling with superintelligent AI. Vinge's science fiction basically remained science fiction.
So, if we connect this to the bigger picture, we finally arrive at the absolute root cause of these historical failures.
The core issue.
There is this embarrassing, cavernous gap between the exponential graph of the futurists and the reality of the laboratory floor. Why did brilliant people like Turing, I.J. Good, Vinge, and Kurzweil all get it so wrong?
Well, they all answered Turing's foundational question. Can machines be smart like people? With a resounding, enthusiastic yes.
But they did so by completely ignoring the fundamental bottleneck that the engineers were constantly hitting their heads against.
Right, and that ultimate obstacle was, and frankly remains, natural language.
Why is language so impossibly hard for a machine? We really need to drill down into the mechanics of this because it is the wall that completely breaks the concept of the singularity.
Okay, let's do it.
Let me give you a classic example used in linguistics to test AI. It's known as a Winograd schema.
Oh, I love these.
Okay, so if I say to you, the city councilman refused the demonstrators a permit because they feared violence, who does the word they refer to?
Well, as a human, you immediately know they refers to the city councilman because councilmen are the ones who would fear violence from demonstrators.
Exactly. It's obvious. But if I change literally one word in that sentence and say, the city councilman refused the demonstrators a permit because they advocated violence, who is they?
Now, they obviously refers to the demonstrators.
Right. But think about what's happening there computationally. The grammatical structure of the sentence is absolutely identical. The pronoun they is exactly the same.
Right.
The only possible way you know the correct answer is by relying on a vast, completely unspoken reservoir of human cultural context about how political protests actually work.
You have to understand the dynamics of civic power, the psychology of crowds, the concept of bureaucracy.
Yes. You have to know what it literally feels like to be afraid of a mob or to be angry enough to protest. You have to have lived a life in a human society.
And a computer, obviously, does not possess a lived human experience.
It just sees syntax. It sees words as dead mathematical tokens to be sorted.
And this failure to make substantive progress on the difficult, ambiguous aspects of natural language is incredibly instructive for the whole field.
It really is. It proves that human cognition simply cannot be separated from human language.
And human language cannot be separated from human biological experience.
Right. The differences between a biological human mind and a silicon machine are infinitely more subtle and complicated than Alan Turing or Ray Kurzweil ever imagined.
They are. The central thesis we've arrived at, based on the source text, is that our use of language is essentially the operating system of our intelligence.
And the entire history of AI research proves that natural language represents a profound, deeply resistant, and perhaps entirely insurmountable theoretical wall for artificial systems. It is literally the wall that the exponential graph crashes into and burns.
Exactly.
So let's take a breath and look at the whole journey we've taken today.
It's been a long one.
We started in the shadow of the nuclear bomb in the 1940s, staring at John von Neumann's terrifying mathematical horizon.
Right. We saw that initial fear that progress would hit a divide by zero error, an asymptote, an infinity where human history just abruptly ends.
We then tracked how that pure mathematical anxiety was hijacked by science fiction writers.
And eventually transformed into a quasi-religious inevitable promise by Ray Kurzweil.
We dissected his so-called law of accelerating returns, and that incredibly aggressive philosophy that views biological humans as nothing more than a temporary stepping stone to a machine destiny.
But finally, we drag that soaring futuristic narrative back down into the dirt of the actual computer science labs.
We saw how the field actually suffered for decades as a degenerating research program,
Wrapping endless layers of duct tape around fundamentally flawed models.
constantly defeated by the immense, subtle, unspoken complexity of human language.
Which leaves us with a final thought to analyze. building directly on the logic of these historical failures.
I think this is the crucial takeaway for the listener.
If human intelligence is intrinsically bound up with natural language,
Which it is.
and natural language is a capability that AI has historically only been able to simulate through semantic parlor tricks and bluffing.
Then the singularity is not an inevitable point on an exponential graph.
No, it is fundamentally a misunderstanding of what a mind actually is. If computer science cannot mathematically map the ambiguous nuances of a single human sentence, by what logic could it possibly map the end of human history?
It brings us right back to that asymptote, that vertical line on Kurzweil's graph.
The line going straight up into infinity.
We look at that line shooting violently upward, and we have been totally conditioned by Silicon Valley to think it's a map pointing toward an omnipotent machine god.
But maybe we're just misreading the data.
Maybe, just like trying to divide by zero on a cheap calculator, that vertical line isn't showing a path to superintelligence at all. Maybe it is just the exact point where our predictive mathematical models break down, throw an error code, and simply fail to comprehend the messy, beautiful reality of being human.
It's a powerful thought to leave on.
It really is. Thank you for joining us on this deep dive. The next time you see a